Alrighty, well thank you very much. So my name's Brett Cameron and David Brinnen, and we'll be talking for roughly the next 40 minutes. Hopefully I won't monopolise all of it. And the title of our talk, as per here, is Next Generation SCADA, Monitoring and Controlling Devices in a Connected World with the Help of Erlang. So it's a little while before we get to the Erlang part. I mean, what I'll do first is just give some background on what SCADA systems are all about, talk a little bit about the Internet of Things, and then talk a little bit about the project that David in particular has been working on, and then I'll hand over to him to do a bit of a demo and talk in more detail about the product that we're developing there. Okay, so I'll probably do a Joe and skip through some slides because, like Joe, I've got too many, although not 140. So what is SCADA? So how many people here are familiar with SCADA systems or have any sort of awareness? Damn, there's always one. So SCADA stands for Supervisory Control and Data Acquisition. I mean, basically what we're talking about here is a software/hardware solution that is used for monitoring and controlling plant equipment. I mean, my first job in the software industry back in 1992 was actually developing software for a power generation company in New Zealand. And they use SCADA systems for controlling the hydro dams, for controlling thermal electricity generation and so forth. And, you know, this was their control centre was like NASA mission control with all these big screens and flashing lights when something broke and so forth. Behind this was a SCADA system that was monitoring and controlling all of that plant equipment. They had the ability to see when things broke. They had the ability to, at the push of a button, control various devices. They were collecting historical data that they could use for various analyses and so forth. So SCADA systems have been around for a long time, and as I say, they're typically used to monitor things and control things like power stations, factories, water and sewerage, refining, all of those sorts of industrial areas. Okay? As time has gone on, I mean, early SCADA systems were probably fairly contained. As time has gone on and we've had advances in network technology and computing and so forth, SCADA systems have now become somewhat more distributed, potentially spanning fairly large geographies and so forth. And now, with the advent of the Internet and the Internet of Things, SCADA systems are potentially global, as we'll see later on. So, in general terms, this is, you know, what a SCADA system looks like. I mean, at the bottom level, you've got some plant, you've got things that actually do stuff, you've got sensors and actuators and other control elements. The next level up in the hierarchy are things like PLCs and RTUs, which send instructions or receive messages from those plant-based devices. And then at level 2, you actually start getting into the sort of software, the computer layer, communicating with those RTUs and PLCs. A little bit more detail on those various bits and pieces. I won't go through them in any particularly great detail. As I say, programmable logic controllers and RTUs actually interfacing with the hardware of your plant, and software communicating with those devices to actually make things happen or to gather data and so forth. Another key component of a SCADA system is obviously some form of user interface, some sort of human-machine interface, so a human can actually see what is going on in near real time, or preferably in real time actually. If it's something like a nuclear power plant, you probably want to know pretty much straight away if there's a problem. So these things typically have some fairly good graphical user interface. The Internet of Things, everybody is talking about it, but you know, what is the Internet of Things? What does it really mean? I wasn't too sure myself, so I consulted the oracle of all knowledge, namely Wikipedia, which told me that the Internet of Things, IoT, I hate these abbreviations, is a network of physical objects or things embedded with electronics, software, sensors, and network connectivity, which enables these objects to collect and exchange data, and so on and so forth. Rather wordy and verbose definition. I mean, basically what we're talking about is just connecting things other than computers to the Internet. Okay? It's maybe a little bit more useful to define what these things are. Okay, so what is an Internet of Things solution and what are these things? So in order for something to be an Internet of Things solution, it must connect. It must connect to the physical world, collecting some information or affecting some sort of change. It must connect to other things in order to interact with them efficiently. Maybe it's monitoring your heart rate or monitoring some piece of plant equipment or whatever. And it must connect to the Internet or some other form of network to disseminate information or possibly to receive instructions. Must do some form of computation. Maybe it's reading some piece of data, doing a manipulation on it or whatever. And it must communicate, which we've talked about before. So at a high level, that's what things are. And, you know, with technological advances and so forth, the numbers of... It's the SCADA guy. What's that the theme tune to? What's that the theme tune to? Oh, geez, it is too. Anyway, so as time has gone on, more and more things, God damn it, our phones, more and more things are being connected. It's easier to have, you know, really energy efficient little devices, millions and millions of these things connected to the internet, transmitting signals back to home base and so forth. And over the past decade or so, there's just been a proliferation of these things. I mean, it's just going berserk, you know. You can have all sorts of fun if you're into electronics. You know, back when I was a kid, electronics was building a crystal set with a diode and a coil. These days, it's doing something funky with a Raspberry Pi and a computer. And, you know, if you start looking at some of the numbers, it's kind of quite interesting. Samsung, they've stated that by 2017, 90% of their goods will be able to connect to the internet and do something, and they're aiming for 100% by 2020. Okay, and in US, I put here that by 2020, nearly 4 billion devices will supposedly be connected to the internet, and nearly 7 billion by 2025. I'm not sure how they measure these things, but I'll take IDC's word for it. And around the 2008 timeframe, depending on who you talk to, the number of things connected to the internet exceeded the number of people on Earth. And by 2020, they're looking at 50 billion internet-connected devices of some form or another. Okay? So all of this Internet of Things stuff, Cisco's CEO stated a fairly large number for what this business is worth, $19 trillion potentially. I mean, that's a lot of money. Could be some good business opportunities in there. So what are the sorts of markets? Where would you go to try and develop a solution to actually get a slice of that $19 trillion pie? These are the sort of emerging markets that we're looking at for Internet of Things type solutions. The ones I've highlighted in green, if I remember correctly, are because they kind of relate to what David will talk about later. The Internet of Things, of course, there's also a lot of challenges and concerns, and not surprisingly, security is at the top of the list. Joe Armstrong mentioned in his talk this morning Alan Kay. I was here in 2016 when Alan talked about not so much the Internet of Things, but just about all of these connected devices. And in particular, he talked quite a lot about the security side of things, that you've got organisations like the NSA potentially wanting backdoors to all of these devices, being able to snoop and eavesdrop on you. That's maybe not such a good thing. But you don't want people hacking into your devices no matter who they are, and you know, maybe changing the temperature in your fridge so that you don't notice and you get salmonella poisoning or something like that. All of these things are possible if you're not careful. And David and I were actually at an event a few weeks ago, and a security guy was doing a talk and was talking about the Internet of Things, and it was really quite disturbing how many unprotected solutions there are out there. So good opportunity for Paul down the back there to help people tighten up in this space. So as I say, security, big area of concern. I mean, I talked about people being able to hack your devices, eavesdrop or whatever. Legislation and policies and so forth is also an important area. I mean, where is this data going? You've got data sovereignty issues, you've got data privacy issues, all sorts of things like that going on. So all of this technology is just happening at a rapid pace, and there's still a lot of this stuff that needs to be sorted out. Energy efficiency and so forth, you've got all of these little devices out there doing stuff. They consume a lot of electricity. That's getting better, not such a big deal, to be honest. From a software development perspective, what are most software engineers doing if they're working in the Internet of Things space? This is a survey from the Eclipse Foundation. What I kind of find interesting is most of them are doing IoT platform, whatever that is, / middleware. I hope that doesn't mean that the largest percentage of people are actually developing middleware, because there are plenty of good middleware solutions available. No need to develop another one. But these sorts of solution areas seem to be the primary areas of focus from a software development perspective at the moment. What's interesting from our perspective in terms of the solution that David will talk about is the fact that there have been fairly big jumps in the past couple of years around industrial automation, energy management and things like that. The sorts of areas that require some sort of SCADA solution. Again, from a developer perspective, what sort of tools, or more to the point, what sort of programming languages are people using? Key point is this one: we need more Erlang. People are doing most of this coding, it would seem, in Java and C++, disturbingly high levels of Python, and so we go on down the list. But there's no Erlang there, we need to get more of it on there. So that should be your mission when you leave today. If you're doing any work in this space, you need to be doing it in Erlang, not in Java or C or Python. This one, not so interesting. I mean, this is at the lower level where you're starting to talk to those RTUs or those PLC devices, industrial messaging protocols. David will talk a little bit more about that. One of the problems you've got in this space is that there are so many different standards, and a lot of these standards are quite old. And you go out and buy these little devices to communicate with your equipment and so forth, and there'll be some clunky old protocol that was designed maybe 20 or 30 years ago, and you're trying to drag that kicking and screaming into the 21st century. I was watching David a couple of Fridays ago, basically having to build gateways between a device that spoke one language to a device that spoke another just to get a temperature measurement. Frustrating. So that's also a common problem in industry, is that quite often things don't change quickly. So in any of these Internet of Things type solutions, you quite often find yourself having to get a little bit creative and deal with a whole pile of old stuff that's been controlling the plant maybe for the past 20 or 30 years, and that the company will just not want to change. You have to figure out a way to interact with it in order to get your solution across the line. Okay, so next generation SCADA and Industry 4.0. Who's heard the term Industry 4.0? Two, sort of. Slowly raises hand. So there have been a number of industrial revolutions, and I've been alive for two of them, which is a bit disturbing now that I think of it. You can deduce that when I say that I mean the last two, right? I had a hard night. Okay, so the first industrial revolution, 1784, which was mechanical production powered by steam and water. I mean, this was a fairly major breakthrough. Industry 2.0, fairly big jump there. 1870, assembly lines, great, and electricity. This made a fairly significant contribution to the advancement of mankind and industry. Industry 3.0 is described as being computers, automation, and distributed control, which is where some of those original SCADA systems come into play. Industry 4.0 now pertains to essentially taking some of this stuff we've got, combining it with things like cloud, big data, real-time analytics, artificial intelligence, data streaming. You just think of all the cool buzzwords and so forth and throw it in there and put it in some sort of industrial context, and you've got Industry 4.0. The term Industry 4.0 apparently comes from the German government, so it's probably not really Industry 4.0, but it's the German equivalent thereof, which I don't know what industry is, but 1, 2, 3, 4, I can do the 4. Anyway, so the German government basically has kicked off this initiative to drive Industry 4.0. And, David and I were at this event 2 weeks ago in Copenhagen. All of the guys there, Siemens, various other companies like that. I mean, this is frame of mind stuff for them. It's kind of all they're talking about is Industry 4.0. How do we do this this new type of automation? How do we hook up Internet of Things technology, software, standards, everything like this? How do we do this Industry 4.0 thing? I found the graphic on the next page here kind of quite amazing. I haven't quite figured out, maybe Norway is just asleep, but like the rest of Europe seem to be doing some cool stuff with this, but either the way the graphic's drawn is Norway's all covered in snow, or they're actually just not getting on board with this stuff. But the bottom line is this whole Industry 4.0 initiative is really kicking off across Europe, and you'll probably start hearing more about it across here, I would say, fairly soon, starting today. So what does all this mean? So Industry 4.0, SCADA systems, the Internet of Things. I mean, where things are at now as far as SCADA, I mean, SCADA is kind of a cool acronym, but basically it's computers interacting with plant equipment via devices and networks and so forth. What we're in a position to do now is to take that to the next level and start leveraging the internet, global scale. These SCADA systems don't necessarily need to be constrained to your city or whatever, the sewage plant in your city. Perhaps we could have some cloud-based solution which is monitoring and controlling sewage plants all across the country. Scary thought if the whole thing went down, I suppose, but yeah, that could be a bit messy. But anyway, basically we're now at a position where we can have these so-called, as I've called it, next generation SCADA systems, where we're leveraging all of these new Internet of Things type technology, basically working with the same problem domain, but being able to do so much more with the information, potentially gathering more information, doing more useful things with it. I'm thinking of Joe's talk this morning where he's saying we're having far too much information. Maybe he's right, we need to build in some purge functionality to get rid of all the crap data. But anyway, that's basically where next generation SCADA comes from. Control machines, so David and I, well mostly David, works for a company called Energy Machines. Energy Machines, I'll describe it naively, David can describe it less naively. Energy Machines basically develop, I refer to them as almost industrial scale heating and cooling, but energy efficient. So you've got energy stores in the ground and so forth. You know, these things are designed to heat and cool hospitals, factories, hotels, large buildings, large facilities like that, and to do it in a very energy efficient way. You know, the hospitals, one of the hospitals that we're working with have saved sufficient funds that they can now employ more people and things like that. So that's great technology, that's the hardware side of things. But in order to actually make that work, you need a way to monitor what's going on, you need a way to control what is going on. And this is what the control machine software does. It works with the Energy Machines hardware to monitor thousands of sensors potentially in real time and make changes where appropriate in order to ensure that everything is optimized all the time. In parallel with that, another one of the engineers has developed a digital twin, essentially, which allows you to simulate how that hospital should be heated or cooled, and that allows us to actually kind of have like a feedback loop going on to even better optimize things. Some squiggly diagrams, David will do a live demo soon, but the key thing here that I've marked in red is the MQTT-based data broker. How many people know what MQTT is? Well, that's good, I won't bother talking about that, that saves me 2 slides. So for those that don't know, MQTT is basically a popular protocol for the Internet of Things. It's a very lightweight pub-sub protocol, and it's designed to work well in potentially constrained or unreliable network environments and things like that. But anyway, within the Energy Machines environment, data is being published into an MQTT broker. We're using for that a thing called EMQ MQTT broker, which is 100% Erlang based. So I know you've all been wondering where the hell does Erlang come into the equation here. So that's where Erlang currently comes into the equation as far as control machines is concerned. And going forward, we're looking at introducing more Erlang technologies. RabbitMQ will be factored into the equation fairly soon, and potentially even look at using Erlang for some of the glue to coordinate all of these bits and pieces. So just a little bit about the EMQ broker, and then I'll get out of the way and let David talk. As I say, 100% Erlang, very nice implementation, massively scalable. And also, you know, if you're at my RabbitMQ talk yesterday, I talked about plugins and so forth. So EMQ provides similar sorts of facilities. You can extend the EMQ broker by developing your own plugins in Erlang to support different protocols, to support different authentication mechanisms and so forth. Don't really need to talk about that because I just did. And we don't need to talk about MQTT because you all know about it, except for this slide. So MQTT was invented by a guy named Andy Stanford Clark, IBM distinguished engineer. And a lot of this is actually all about mousetraps, where Andy has an old house on the Isle of Wight, if I recall, and you know, he has pesky little rodents and so forth. So the original versions of MQTT were really Andy wanting to monitor things like his mousetraps. He travels often. He also wanted to monitor whether his plants needed watering and so forth. And this was kind of the genesis of the MQTT protocol, rather ironically. And it's now become probably one of the most dominant protocols for these Internet of Things style of solutions. Anyway, enough of me. We'll let David talk about the fun stuff.
start with, I'm from Sweden, and I did my education at the Royal Institute of Technology in the Chess town in Sweden, probably stand on the Ericsson to be. And I didn't have the opportunity to learn Erlang as my first language. I did Java as the first one. You should keep your enemies closest and your friends on the second level, right? So control machines is the, what we call it, next generation SCADA. We take it to the next step in terms of connect stuff, how you analyze the data from the plants and make the plants operate more efficient by help of energy engineers, people that knows the energy thermal equations and so on. And yes, you heard the SCADA. First time my boss asked me about this SCADA project 4 years ago, I thought it's told me Scala, which is the programming language. And it's a Java Erlang-like programming language. But yeah, it's SCADA. And yeah, I was very new to it. And why? Yes, as Brett mentioned, is to actually to visualize our products in terms of the heat pump and integrated energy systems to provide the big facilities with heat and cool, or the client machines, the air handling unit, to provide also big facilities with fresh air. And to give us, as operators, to be able to integrate with them and make them run as good as possible. We have one plant in the northern Sweden, we actually cut the power usage by half. And that's megawatts of size. And that's good, not just only for the money for the company, but also for the CO2 emission. We just have one planet, so we should make sure it's run efficient. Yeah, and also you will see, we're not just strict to our own products. We can actually supervise or control anything. Like Sebastian's talk yesterday on the GRIS board, we can just make sure we can communicate and we can have that also up and running, or another IoT devices. And also, like Brett mentioned, my colleague Lasse is working on this simulation tool, which will be the digital twins of our plants or another plant, to make it like as a feedback loop with machine learnings, algorithms, and so on, make them run even more efficient. So yeah, how does control machines work? I just put some 4 icons here, and we can have like 4 module-based software here. That we have the one runtime, the gear on your left side, and then we have a storage module, and then we have a gateway or communicator on your right side, and then we have an agent on the end and on the bottom. And the agent is the Erlang part of this one. And as Brett said, we also investigate how to put more Erlang in the other parts of the software, if we found it's a good fit, of course. And yeah, as you soon will see, there are a lot of different sensors data going from left to right and everywhere. And that's why we have selected to use the MQTT protocol to send this data from one plant to the cloud and from another plant to another cloud, or cloud versus. And we use different brokers to separate also the permissions to update set points for plants, or just to read the data, also subscribe to sensor data or alarms. So all of the plants we actually have this agent and local storage for buffering data or like redundancy of data. And then we have this gateway or communicator which talks to the PLCs, which have this wired or connected to the pumps or valves or compressors or fans, or another IoT device. Today we support the Modbus TSPI protocol, which is a very old protocol from the 70s. It works like a direct map memory. You pull on a register and you get back the value. Or you write to the register and the PLCs start to use the new value, like a set point for a pump speed, for example. Yes. So yeah, and you zoom out, you see these two clouds here. I want to just point out here that we're working with big companies that they don't, for security reasons, they don't want our cloud we use for analyzing the plants to be able to write set points values, because it could shut down the power plant of the hospital, for example, or the hotel. And also, we connect the simulated plants, the digital twins, by these agents spread across the world. And all connected with the EMQ implementation of the MQTT, which is Erlang. And as this is the very, very core of the architecture, I think, yeah. As Erlang, the community here should be very proud, because it's, yeah, as you know, it works. And if it crashes, it gets up and running again. So yeah, I'll just go into a use case of the controlmachines.com to actually visualize some of these plants in real time, and also show you how you can design these plants, as we are looking into to release control machines as a GUI for people to connect their IoT devices quite soon. But yeah, for security, we're using SSL, TSL to encrypt the data. Then we also have some SSH channel there to encrypt the data. And otherwise, we also use some two-step verification to be able to log in to the plants to actually set the set point. For example, a YubiKey one-time password. So yeah, and this is a web application. For software, it's Java-based and Tomcat. And then it's, yeah, all HTML5 and CSS and JavaScript, so it should run on any device. And the picture we see is SVG-based, so they scale to the very small or to the very big. And that's good, because if you go to a plant and see, you can take this plant, for example. It can be quite a lot of values. I don't see if you see in the back now, but yeah, this is, yeah, the wiring is tubes, and in the tubes is fluid water, and you have a lot of different sensors logging temperatures, pressures. You see the circle in the middle is a pump, which is running on 34%, for example. And we can even go into the machine that we have even more sensors to log and monitor how it's performing. Now it's not any compressor. Yeah, now actually a compressor is going to start in the circuit 1 in the top. As you can see, the expansion valve is opening, and then you have the compressor 2 starting. And this is real time. I didn't do anything. And yeah, so this is it. Control machines, and I will show you how it works now, and some of the new features we've been working on to take the next step of SCADA. It was just one person here that actually knows about the SCADA software, but it's been around since the 70s, and I was introduced for this business 4 years ago, and I would like to say it haven't happened so much in this area, which is a good opportunity for us, because we can make it much better. And we have to keep track on to have it more secure and be running anywhere or on any devices. So I will just start to show you the control machines IDE, which is now Eclipse-based, but we are developing to make it the whole as a web application. Development environment, and I have used a simple Modbus simulator here, which is we're acting as a PLC today. It has several different registers. I cannot show you all of these now, but yeah, it's a direct memory. On address 0, you have a value, and this is a digital one, so you can make it to be value 1. For example, or you can just have holding registers, which is 16-bit integers. So yeah, it's Modbus and it's very old. But yeah, you can combine 16 bits to be 32 bits and floating representation as well. But here I actually have I set up a device which have an IP address, and then you create some tags. And I just created some tags, and then on this page I can actually put them on the page and connect the values to the objects. And this can be run then in the web browser. So any change I do will be updated in real time. And now I wrote this value number 1 to this holding address index number 1. And I can change it from the SCADA. Yeah, I wasn't logged in, so I couldn't change it. But if I log in, and it should be like BMS. I will log in. Yeah. And I will actually change the value, so I will use my digital key to enter this. There we go. So yeah. We have 100, and we can double check it was right back 100. Yeah. Easy peasy Japanese. It's nothing that is revolutionary or anything. It's a simulator, and just a demo how it works. And what we have seen with control machines and the SCADA, that we don't just want to be able to control and monitor old PLCs, we also want to connect different internet services to it, like a weather forecast, because you don't want to run the plant on 100% if you know it will be a sunny day next morning, right? The building will be heated anyway by the sun. So that's why we also have by just using now like virtual tags, which can actually be subscribing for an API, third-party API. Like we have connected the Swedish Meteorology Institute, which do the weather forecast for Sweden country, by use a JavaScript API. And I don't know if you can see this one. Yeah, maybe it's not that interesting. But yeah, it's just some regular JavaScript that you actually say that I want to have the forecast date of the weather tomorrow, get date today, and +1, it will be the tomorrow date. And then I specify the longitude and latitude coordinates. And this is a virtual tag and a weather forecast for our office in Malmö in Sweden. And if we go back to see here, it should be like -2.4 Celsius tomorrow, which in Fahrenheit is 27.8. And I would like to stay here longer, I can say. And how did I do the Fahrenheit conversation? Yeah, I just created a new virtual tag, which is based on the original forecast tag, and then I put the math equation. You multiply by 9 divided by 5, and then you add 32 to it, right? And all of these interfaces, it makes it possible to harvest the internet for information and use it to make your industrial plant to run more efficient, or you use your own house by the smart home integration, because these values can be written down to your IoT device or your PC or whatever you have. And more of this is coming in terms of service to use. I don't think the United States have something we have in Sweden, but the Swedish Energy Department have something called CSAR, which is a protocol that the people that have solar panels or windmills, which generate more power than they need, so they put it back to the grid, will have money back, depending on how much they have created in terms of power. So that is also what's coming for control machines, so they can get money back of the good, and so on. And that's the development. But I also would like to go back to to the plant, actually, because we are harvesting a lot of data now. This is on every 5 seconds we store the data. It could be every second, but this PLC running this machine is limited to put all of this data out on a 5-second base. So what we also do that all the data we store, we can go back to any time to see how the machine was operating then. And this is for the analytics part, of course. If we have some problems or we see that our efficiency is not that high as we would have to be during the circumstances. Now this data is updating for every minute. I could make it to be every hour. You see the values going up and down. Or I can just make it like to be every second or 5 seconds. And this is a lot of data. And with this data, you can actually hook up some machine learning algorithms to, as I told you before, to make it even better. And I forgot to translate these pages, but we are also supporting, of course, multi-languages interfaces. So this is the Swedish words for evaporation and conditioning. As you see now, this is a heat pump, which I have a cold side, which is the blue colors, and the red side, which is the heat side, hot side. And in an integrated energy system, you will use these two sides by its nature. And the cool side can be used to chill down a data center, for example. And the hot side could be used for the tap water or space heating. But also, you know, if you have a data center, you want to use the exhaust heat from the data center to use for the heating of space in the closed buildings, right? This is not a data center, this is a spa. So here we got used the water to hot up the pools. But the cold side is used for chilling the supermarket in the same building, the refrigerators. So and COP down in the left corner says it's a coefficient of power, meaning that we're now using 26 kilowatts of power to run the machine. And 1 week back, we had generated 6 times more cool and heat. So, and it can be better. It could be worse. Normal district heating, you just have a COP of 1 or maybe 2. So it's a lot to do here in this energy efficiency, which was one of the points Jan Armstrong pointed out that we should spend more time on. So I'm very lucky to be able to work with this. I'm also very lucky to learn Erlang quite early in my career. I was using Erlang 14b back in 2011. So I think that's round up what I had to say about control machines. And is there any questions from you to me or Brett? We can gladly, 3 questions. We start with the back. You was the first.
Sure. So it sounds like you have an Modbus MQTT gateway on the edge. When you ship your data across, are you packing it up as coils and registers and transforming the coils and registers once they come across after they come out of your MQTT broker?
Yes. We have this, so you see the gear and the storage. These modules convert the data from the device-based format to be a general format for us to store in the database.
And so when it's on the wire with MQTT, it's coils and registers, and then it comes out and it's transformed?
Yes.
I mean, one other point to note there as well is that, like David said, I mean, these things can be spitting out data values once a second. But, quite often the values don't change. It could be 20 degrees for the next 2 days. So there's no point in wasting network bandwidth pushing every single piece of data across the network if the value hasn't actually changed. Yeah. So, we make sure that we do not do that.
So the gateways are smart and don't push on no change?
Correct.
Yeah. It's change on value, what is called in the,
And there's also, localized buffering actually at the site as well, because, you you could lose network connectivity to these things and so forth. So I think it can buffer up to a couple of days or something.
Yeah, I mean the storage is cheap nowadays. I mean you can have a terabyte of disk, so you can actually buffer up quite a lot. But this small device that we just have an SD card for memory, then you could just be limited to be storing 1 or 2 days of data if you have an internet connection issue. Yeah.
Still time. So this is which questions, but for your configuration, you guys looked at something like Node-RED, which is a very graphical, open source configuration service. You write all your stuff in Node or JavaScript, similar to that.
Yeah.
Connect different devices.
There's also a lot of different graphical representation of data. We have some I didn't show you now, but trending data and so on. We also use the high charge, which is
the energy standard here, it's kind of cheesy marketing term, but it's called green button. It's an XML format for reporting energy data, and historic and real time. But that's on the energy companies to start reporting that data. There's a long authentication flow for allowing third-party access to your data. A little more residential focused, maybe. There's standards.
I mean, that sort of thing potentially relates to what David was saying about, future extensions. So, for example, at the moment, hooking in things like the weather service, so that's pulling in information. But there's also that transactional thing potentially where, there's some blockchain type initiatives in the IoT space for handling, essentially microtransactions in terms of selling energy that you're potentially pushing back into the grid and things like that.
I've got a nerve-based Elixir Raspberry Pi that does a lot of this for residential. So HVAC, energy, we actually talked weather stations, building, tile that together.
Right.
cool.
There's only no more time for questions. Yes,
sir. Right. But yeah, we are around, so please have the question otherwise.
Be around, please find it.
Yeah.